Good morning, ladies and gentlemen. It is our pleasure to have today among us Professor Stephen Rose from the Department of Mathematics at University College London. Professor Rose, in fact, graduated initially with a degree in the English language, in the English literature. He spent some time teaching English and the history of ideas, and then went to study mathematics in the University College London, where he graduated, and then he joined the Department of Mathematics of this university, where he is presently teaching the history of mathematics. What I find it very interesting and in some sense fascinating is that he somehow specializes in the history of non-Euclidean geometry, including works by Lobachevsky, Gauss, and Bolyai, and probably some others. In this respect, Professor Rose wrote a remarkable article about the work by Babeş-Bolyai, the appendix. He took the great effort to go through the entire work and present it in a modern language, if I understand correctly. And I highly recommend, especially all those interested in mathematics and the history of mathematics, to have a look at this work, which presents the work by Bolyai from an entirely modern perspective, and to my knowledge is the only work of this type done in this field. And today Professor Rose will give us a talk on the title Great Minds Think Alike, which will also be moving to the presentation of the foundations of non-Euclidean geometry, I guess, with an emphasis on the work by Bolyai. So let's welcome Professor Rose. The floor is yours.
Thank you very much. Well, good morning, everybody. It's a great pleasure to be speaking here in the birthplace of one of the founders of non-Euclidean geometry, and I'm very grateful to Tiberio for giving me this opportunity. So, the discovery of non-Euclidean geometry can be regarded possibly as the most important mathematical event of the 19th century. And the three individuals who are associated with this discovery are, of course, Gauss and Lobachevsky and Janusz Bolyai. Gauss almost certainly anticipated the other two, but it's not entirely clear when he did this and how much he knew. He did state in 1823 that he'd solved every problem regarding hyperbolic non-Euclidean geometry. In fact, he invented the term non-Euclidean geometry. He said he'd solved every problem to his own satisfaction, with the exception of one, which was the determination of a certain linear constant. But Gauss was unwilling to publish his ideas for fear of attracting notoriety. He didn't really wish to appear in the newspapers as somebody saying that Euclid was wrong or that there was a different geometry to Euclid's. And so what ideas he had, he communicated on conditions of strictest confidence to a small circle of correspondence. So it's very difficult to gauge the precise extent of his contribution, and therefore really credit must go to Lobachevsky and Bolyai, who were the first to publish. And so what I'm going to say today really will concentrate on their work. Lobachevsky gave a talk to his colleagues at the University of Kazan in 1826. The detail, apparently it was well received, but the details of what he said have not survived. And then in 1829, he published an article on the principles of geometry where he laid out some of his ideas. This was written in Russian, and it was published in the local newspaper, the Kazan Messenger, but it didn't seem to excite any interest. Thereafter, he wrote several more publications, of which the most important is Geometrical Investigations of 1840. He wrote that in German in the hope of attracting a wider audience, and indeed it did. Gauss himself read it and was greatly impressed, and he praised Lobachevsky's mastery. But typically, Gauss said that it didn't teach him anything that he didn't already know. Nevertheless, he proposed Lobachevsky for membership of the Göttingen Academy, which is more than he ever did for János Bolyai, which is rather strange. But unknown to both Gauss and Lobachevsky, Bolyai was working on the same material. And in 1823, he wrote an excited letter to his father Farkas saying that he had created a new world out of nothing. And his manuscript was finished by 1826, but there was a delay in publication. It's not entirely clear why. Some say it was because his father was not happy with the notion of a linear constant. But whatever the truth of this is, it was finally published as an appendix to a textbook written by his father, and this was published in 1831, and a copy was sent to Gauss. Apparently it was mislaid, and eventually it arrived in Gauss's hands in, I think, January 1832. And Gauss replied. And what he actually said, these are very famous words which I'm sure will be familiar to many of you here. He said, to praise it would amount to praising myself for the entire content of the work, the path which your son has taken, because the letter was addressed to Farkas, the results to which he has led coincide almost exactly with my own meditations, which have occupied my mind for 30 to 35 years. As you can imagine, Bolyai was absolutely devastated, for he believed that he had single-handedly revolutionized geometry, and there was Gauss saying, well, actually, I know it all. He thought that Gauss might be lying. He even suspected his own father, Farkas, of having secretly communicated his ideas to Gauss, who was now dishonestly claiming priority. Bolyai attempted to... Do I just need to do that? Bolyai attempted to gain some recognition for his work. He submitted it to the military authorities in Vienna, and they were unable to understand his work. Not very surprising, because even Gauss himself said that he found it quite hard going, and yet he was even familiar with the material. He actually described János Bolyai as a genius of the first rank, in fact, though he didn't do anything for him. And as I'm sure you all know, János Bolyai took early retirement from the Austrian army, and he retired to Transylvania. He still continued his mathematical studies, but published nothing more. And then in 1848, he obtained a copy of Lobachevsky's Geometrical Investigations, and he was absolutely astonished that another mathematician had arrived at the same results as him. And he commented here, the nature of real truth cannot but be one and the same in Marosvashaheli as in Kamchatka or the moon, or to be brief, anywhere in the world, and what one finite, sensible being discovers can also, not impossibly, be discovered by another. I'll perhaps come back to that. Well, the parallels, if you'll forgive the pun, between the work of Bolyai and Lobachevsky are really extraordinary. Some of their theorems and even some of the diagrams are very, very similar. Coincidence of this kind is not without precedence in the history of mathematics. You only have to think of Fermat and Descartes, who independently discovered analytic geometry, or even more famously, Newton and Leibniz in calculus. So when we ask how is it possible that great minds can think alike, because that's the phrase in English, I suppose the natural recourse is to consider the background, to see what they might have inherited from their predecessors. Well, in the case of non-Euclidean geometry, the background, of course, is the attempt over 2,000 years to prove Euclid's parallel postulate. Euclid's parallel postulate, as you all know, says that given two lines, M and N, intersected by a transversal, if the interior angles alpha and beta, when summed, come to less than two right angles, then M and N will meet on that side where the sum is less than two right angles. Now, the thing is that Euclid's successors over 2,000 years were unwilling to accept Euclid's view that this was an assumption, take it or leave it. They believed that it was an unproved theorem, and so they set about trying to prove it, to derive the parallel postulate from Euclid's first four postulates. And their attempts to do so took many forms, more often than not trying to prove an equivalent formulation to Euclid's. One of the most common would be the formulation known as Playfair's axiom, given a line and a point, not on a line in a plane, only one straight line can be drawn through the point parallel to the given line. This was a common way of trying to prove Euclid's parallel postulate. Another one, which we find in Islamic mathematics, is the one given by Alhazen. Alhazen is the medieval English name for Ibn al-Haytham. And he wanted to prove the parallel postulate by showing that if you had a quadrilateral with three right angles, then the fourth angle would necessarily have to be a right angle as well. All these attempts to prove the parallel postulate failed. Usually, not exclusively, but usually because at some point in the argument, the mathematicians included an assumption equivalent to the parallel postulate itself, which had turned up in an unexpectedly new disguise, which rendered their arguments circular. So, nevertheless, some of these failed attempts were very interesting. And amongst these neo-Euclideans, we can pick out two who... We can pick out two who could be said to have directly influenced the discovery of non-Euclidean geometry. One of them was Girolamo Saccheri, an Italian Jesuit priest, blindfold chess champion, and professor of mathematics at the University of Pavia. He was a convinced Euclidean, and in his treatise Euclid Freed from Every Flaw, he set out to prove the parallel postulate by Szekely started with what is now called the Szekely quadrilateral. This is a quadrilateral with 2 right angles at the base and equal sides, and it was easy to prove, without using the parallel postulate, that the summit angles were equal. But equal to what? If they were equal to a right angle, which he called the hypothesis of the right angle, which he also showed was logically equivalent to the proposition that the angles of a triangle add up to 2 right angles, then if you could prove that, then you would also prove the parallel postulate. But there were 2 other possibilities as well. The hypothesis of the obtuse angle, whereby the angles of a triangle would exceed 2 right angles, or the hypothesis of the acute angle, where the angle sum would fall short of 2 right angles. And his aim was to prove this by disproving these 2. Well, he succeeded in refuting the hypothesis of the obtuse angle. He showed that actually that did contradict Euclid's first 4 postulates. His attempt to disprove the hypothesis of the acute angle failed, but it failed in a very illuminating way. In order to get a contradiction, Szekely came up with this configuration. So what we have here is a series of quadrilaterals with 3 right angles and an increasingly acute angle at A. And these rays AL, AM, AN all have increasingly small common perpendiculars with this side BX, and X is to be regarded as an infinite point. And while there is no last ray, there is a limiting ray, and the lower limit of all these rays would be AX. At the same time, Szekely said, there are clearly many lines which intersect BX, AB, AF, AG, and so on. And although there is no last intersecting line, there is clearly going to be a limit, and the limit will be the same ray, AX. And that, said Szekely, gives me my contradiction, because the same line, AX, cannot both share a common perpendicular with BX and yet intersect it, because lines that have a common perpendicular by Euclid's theorem 127 must be parallel. His mistake, of course, was to apply Euclid's theorem, which is designed to express the relationship of finite lines, to infinitely extended lines. He's actually treating an ideal point at X as if it were an ordinary point. But what he actually has done here is that he has given a representation of the hyperbolic plane, because this line AX, which separates the non-intersecting lines from the intersecting lines, is precisely the asymptotic parallel discovered by Gauss and Bolyai and Lobachevsky. But it was, I think, his passionate commitment to Euclid which prevented him from seeing what it was that he had done and taking his exploration further. The second important figure, if I can, is Johann Lambert. So Johann Lambert is a Swiss mathematician, scientist, and philosopher who ended his career with Euler's recommendation at the Berlin Academy. He was a little bit more cautious than Szekely. He refuted the hypothesis of the obtuse angle in a different way from Szekely, but he recognized that the hypothesis of the acute angle was much more difficult to deal with. He said it doesn't refute itself very easily. And what he discovered was that, contrary to a long-standing assumption about geometry, there exists a linear constant relating distance to angle measure. And he found this in two different ways. He first considered a quadrilateral with 3 right angles and an acute angle, where these two sides are equal. And what he was able to show was that the acute angle at G determines the size of the quadrilateral and therefore determines the length of AB and AD. So that suggests immediately that you can express distance in terms of angle. And if you could find the constant there, then that would be the linear constant, which crops up, as we'll see in a moment, in Bolyai and Lobachevsky. He also discovered that on the assumption that the hypothesis of the acute angle is true and that the angle sum is less than 2 right angles, he also showed that the defect of a triangle, the amount by which its angle sum falls short of 2 right angles, is proportional to its size. He showed this really very simply. We take a triangle here, A, B, C. We divide it into 4 smaller triangles. We suppose, under the hypothesis of the acute angle, that the defect of these smaller triangles is alpha, beta, gamma, and delta. And then we see that the angle sum of triangle ABC is going to be all the angles here. So that's going to be 2 right angles minus the defect in the first, 2 right angles minus the defect in the second, and the third, and the fourth. And then take away the 6 right angles that we've included here, the 3 lots of 3 adjacent angles. And it turns out, with just a little bit of addition, that the angle sum of ABC is 2 right angles minus the sum of the defects of all the others. And it was easy to show, therefore, with a rather simple argument, that this was actually a linear proportion. And lastly, Lambert came up with a really quite perceptive and prophetic remark. He said that the hypothesis of the acute angle would be valid on the surface of an imaginary sphere. He didn't really explain this, but it's been suggested, and it's almost certainly true, that what he did is that he looked at the area of a sphere, of a spherical triangle, ABC, and of course on the sphere, the angle with a spherical triangle, the sum of the angles exceeds 2 right angles. And he noted that you could transform this formula in spherical trigonometry to the formula to a formula in hyperbolic geometry simply by substituting ik for k. It simply reverses all the signs. So if you had a sphere and pretended it was an imaginary sphere, lo and behold, you end up with the hypothesis of the acute angle. This turned out to be a rather important and prophetic remark. Work of Sakary and Lambert was very interesting, but it provided more questions than answers. By the end of the 1700s, really geometry was in disarray. D'Alembert said that the theory of parallels was the great scandal of geometry because the whole edifice of Euclidean geometry depended on a supposed theorem, the parallel postulate, which no one could prove. And one of the most puzzling aspects of this conundrum was that one alternative to the parallel postulate, namely the hypothesis of the obtuse angle, had been refuted, but the hypothesis of the acute angle continued to resist all attempts at refutation. Gauss described it as this hypothesis as the reef in the water on which all the shipwrecks occur. This impasse finally led Gauss and Lobachevsky and Bolyai to explore the idea of a geometry based on the hypothesis of the acute angle. I suppose the phrase that comes to mind in English is, if you can't beat them, join them. Maybe you have an equivalent in Hungarian and Romanian. So in effect, Gauss and Bolyai and Lobachevsky went over to the other side and said, okay, let's see what happens if we have a geometry where the hypothesis of the acute angle is valid. And what they did is they substituted, for the parallel postulate, they substituted something that we might call the hyperbolic postulate, which is a reforming of Playfair's axiom. In a plane given a straight line and a point not on the line, more than one straight line can be drawn through the point which fails to meet the given line. Many of the early theorems of hyperbolic non-Euclidean geometry are almost natural consequences of this hyperbolic postulate. So it's no surprise that these theorems appear in both the work of Bolyai and Lobachevsky. So let's just consider a few of them here. And you'll forgive me if what I say is, very familiar to you, but I'd rather be obvious than not understood at all. So clearly, right. Okay, if we start with a straight line and a point not on the line, and we make sure that this is perpendicular to this, then clearly we can draw a line perpendicular to the perpendicular, and Euclid's theorem 127 assures us that these two lines having a common perpendicular must be parallel. At this point, we invoke the hyperbolic postulate and we say, okay, there's at least one more line that we can draw through our point here, which fails to meet our given line. Of course, if there's one, then there must be an infinite number of such lines, because we can draw many of them through here. And they can't possibly cross the first one, because that would contradict Euclid's first postulate that only one straight line can be drawn between any 2 points. At the same time, of course, there are clearly lines through the point which intersect, like this perpendicular, and we can draw many others. And it follows that there must be a dividing line, a boundary parallel, which separates the non-intersecting from the intersecting lines. And this is the parallel defined in hyperbolic geometry. And clearly, if there is one on the right, then there will also be one on the left. And a diagram like this appears both, this diagram is actually taken from Lobachevsky, but something similar can be found in the work of Bolyai, and indeed Gauss, because one or two things of his have remained. And both Bolyai and Lobachevsky became interested in the angle which this boundary parallel makes with the perpendicular. And Lobachevsky invented the notation that if we have a point here which lies at a distance p, the angle of parallelism will be written by capital pi p. This notation doesn't exist in Bolyai's work, but it's sort of generally accepted nowadays. And they both noted that the angle of parallelism decreases as the point moves away from the given line. They didn't even think it worth explaining this because it seemed to them pretty obvious, but you can prove it quite easily here. If you take a point here and you take another point here, and we call this angle 1, call this angle 2, and call this angle 3. Well, we know, because the sum of the interior angles between two lines that are parallel must be less than two right angles, we know that 1 plus 2 has got to be less than 2r. But at the same time, we know that 2 plus 3 being adjacent angles has to equal two right angles, and therefore 1 must be less than 3. And in actual fact, this is clearly stated in Lobachevsky's work and assumed by Bolyai as well. As the point moves to infinity, the angle of parallelism tends to 0. But as the point P moves closer to the given line, the angle of parallelism approaches, it becomes flatter and approaches a right angle, which is, of course, the Euclidean figure for the angle of parallelism. And this gave both Bolyai and Lobachevsky the idea that over infinitely small domains, hyperbolic geometry merges into Euclidean geometry. And this, of course, enabled Bolyai actually to introduce the infinitesimal calculus in the latter part of his work, knowing that over small domains, various identities of Euclidean geometry will be true. Okay, so as we can see, so far everything is pretty natural, and it's no surprise that we see these two great minds thinking alike. Now, by analogy with a circle which intersects the radii at right angles, it was then natural for both Bolyai and Lobachevsky to conceive of a curve which intersects each one of a sheaf of parallel lines at right angles. And Bolyai called this an L line, and Lobachevsky called it a horocycle, and Lobachevsky's term seems to have stuck. Gauss actually called it a paracycle. But, and of course, once you've got a horocycle like that, it then becomes natural, doesn't it, to think of concentric horocycles. And then it becomes almost natural to wonder about the ratio of this arc of a horocycle compared to this arc when they're stretched between two parallel lines. There we are. And it was obvious to both mathematicians that the ratio of one arc to another must be a function of the radial distance between them. You can see that the arcs obviously get smaller, and they both proved that the ratio would just be a function of this. And then from that, they concluded that the function relating one arc to the next must be the exponential function. And they used very similar reasoning to do this, so that if we have A, B, what have we got there? C, D, and G, K. And we suppose that the distance between A and C is a distance x, and the distance between C and G is a distance y. Then it would follow that arc AB over arc GK would be some function of this distance, which would be x plus y. But we can also see, can't we, that AB over GK is equal to AB over CD times CD over GK, which equals f of x times f of y. So it appears that f of x plus y equals f of x times f of y. And the solution to this functional equation must be that f has got to be equal to some exponential function a to the x for some a greater than 1. Now at this point, Bolyai and Lobachevsky moved in slightly different directions. Lobachevsky said, okay, f is equal to a to the x. But of course, this x is an actual distance. It's not a number. And therefore, we can express this distance in any unit of measurement we want, including one that simply allows us to write a as Euler's e. And therefore, Lobachevsky said, we can just call this e to the x, and this x is any suitable unit of measurement which makes this true. Bolyai implicitly, because he doesn't actually do this in the text, but implicitly he suggests that a is equal to e to the 1 over k for some k. And then it appears, therefore, that a to the x will be e to the x over k. And so here we see for the first time in Bolyai's work the presence of this letter k, which is the linear constant. Actually, Bolyai wrote it as I, which is very confusing. It was Gauss who used the letter k, and now everybody uses the letter k in order not to confuse it with the square root of -1. It seems very odd that Bolyai did something as crazy as that. And he noted, of course, that if x actually equals k, then the ratio of this to this will simply be e to 1. And therefore, this enabled Bolyai to define the linear constant as the radial distance between two horocyclic arcs, such that the ratio of the larger to the smaller is Euler's e. And later on in his treatise, he actually proved this in another way. Okay. So far, fairly natural. By analogy with a circle, where a circle can be rotated about one of its axes to produce a sphere. So quite naturally, Bolyai and Lobachevsky thought we can rotate a horocycle about any one of its parallel axes to create a three-dimensional figure. And this is the most extraordinary coincidence between the two, because this is Bolyai's diagram, and you can see that he has got a right-angled triangular prism whose edges at one end converge towards an infinitely distant point, and at the other they intersect with the horosphere, which has been created by rotating a horocycle about one of its axes. And it intersects the horosphere in a horocyclic triangle ECD. In the same way, Lobachevsky's right-angled triangular prism with a right angle along C, it's the other way up because its edges converge to an infinitely distant point there. They intersect the horosphere in the horocyclic triangle AFE. And you notice as well that both mathematicians have very cleverly embedded a plane triangle inside the triangular prism in such a way that the triangle and the horocyclic triangle have a right angle in common. This is a right angle and this is a right angle. And they also have one other angle in common. This angle here at A is both the angle of the horocyclic triangle and the area of the plane triangle. And the same is true in Bolyai's, similar in Bolyai's. And of course, the reason they've done that is that they want to use information about the horocyclic triangle in order to derive the properties of the triangle in the hyperbolic plane. What both mathematicians discovered is the astonishing fact that the geometry of the horosphere is Euclidean if horocycles are substituted for straight lines. So, for example, in this horocyclic triangle, the angles will add up to two right angles, and all the other theorems of Euclidean geometry are true. This was particularly important because what both mathematicians wanted to do was to do some trigonometry. Unfortunately, if you abandon Euclid's parallel postulate, you abandon the notion of similar triangles, and therefore that undermines plane trigonometry, so you've got a problem. The horocyclic triangle rescues it because you can use the Euclidean properties of the horocyclic triangle to derive the trigonometric identities of the plane triangle. You don't have to do it this way, but that's the way in which they did it. And this allowed them to do two things. One, they were able to derive the identities of spherical trigonometry and thereby show that spherical trigonometry is independent of the parallel postulate, very important result. And secondly, it enabled them to derive the identities of the hyperbolic plane, of which the most important is this one here, because of course we had, did we not, that we had a distance p and we have an angle of parallelism which is a function of that, and both mathematicians came up with this relationship that the tangent of half the angle of parallelism is equal to e to the power of minus p over k, where k is the linear constant. Now, at this point, it becomes much more difficult, because everything up to now you could consider a natural consequence of the hyperbolic postulate. But this is not really natural. This is actually rather a complicated formula that's not at all obvious. And in actual fact, Bolyai and Lobachevsky proved it in quite different ways. Bolyai's proof is really quite extraordinary. Here he's got a triply asymptotic triangle, so we're to think of these vertices at infinitely distant points. He's got a horocycle centered at the top here, which is this one. He's got various horocycles drawn centered at this infinitely distant point. And he uses at least 3 previous lemmas to show that this is the most important bit of it is here. Here we've got NB, which is parallel to MA. The distance between them is Y. And what he's able to show is that an angle U here is half of the angle of parallelism, and he's able to show that the cotangent of half of U here is equal to e to the power of y over k, or tan would be equal to e to the minus y over k. I won't go into the details. All I wanted to say was that it's really quite complicated. Lobachevsky's idea was different. He doesn't actually use horocycles at all. He uses a right-angled triangle. These angles are expressed as angles of parallelism. We're to suppose that this angle here is the angle of parallelism corresponding to some arbitrary length beta. And this one is the angle corresponding to some arbitrary length alpha. What he does is he takes the right-angled triangle, he extends CB to B dash, he draws A to A dash parallel to this. This angle here is vertically opposite, so this will also be the angle of parallelism for beta. He extends this amount here by that quantity beta, and then at that point draws DD perpendicular. And from that, you can see by inspection almost that pi of beta equals pi of alpha plus pi of c plus beta. He then takes another triangle and extends it in the opposite direction, and he ends up with this equation. I'm glossing over the details because the details themselves are not quite what I want to talk about. Subtracting these, you get this equation. Adding them, you get this equation. You take the cosine of everything on the left and the cosine of everything on the right, similarly for the second equation, and you divide the first equation by the second, and you end up with this rather messy bit. He then simplifies it by using an identity which he had previously derived, one of the identities of a right-angled triangle in the hyperbolic plane, and he ends up with this. And then he notices that these cosines can be expressed using a half-angle formula in terms of tangents. At this point, Lobachevsky's argument becomes a bit messy, but in effect, you can see that we've got a functional equation here. Some function squared is equal to the product of two other functions, and that suggests, just like last time, that the function must be an exponential function, and he ends up with the same formula as Bolyai. Now, the point I wanted to make is this. It's impossible to believe that either Lobachevsky or Bolyai derived this fundamental identity in the same way as they proved it. They almost certainly knew the answer beforehand in order to make the derivation possible, because as Archimedes says in his preface to the method, it's easier when we have previously acquired some knowledge of the question to supply the proof than it is to find it without any previous knowledge, which I think is a nice remark. So the question is, how do they do it? I don't think we can answer this definitively unless we could actually see their mathematical notebooks and see where they were, what they were doing, what they were crossing out. But a hint could possibly be found from the work of an earlier contemporary, Franz Turinus. Franz Turinus, in 1826, had invented something that he called a log spherical geometry. And he seems to have taken up Lambert's idea of taking the identities of spherical trigonometry and replacing the radius by an imaginary radius. And if we substitute ik for k, then you can transform the fundamental, one of the fundamental identities of spherical trigonometry into this hyperbolic formula quite easily, because of course the cos just goes into the hyperbolic cosine. And if you take a special case of this, which is what Turinus did, if you take the special case where A is an infinitesimally small angle approaching zero, and this side BA is therefore an asymptotic parallel. And if you take C as a right angle, what you find is that the hyperbolic formula here just reduces to this. Because of course the cosine of a right angle is going to be 0 and the sine of a right angle is going to be 1. And you just get this. And that, in actual fact, is an alternative form of the fundamental identity of hyperbolic geometry. It's easy to show that that equates to that. Now, there's no proof that Bolyai and Lobachevsky were familiar with Turinus's work. He only published his book in 1826. It didn't arouse any interest at all. He was so upset that, in fact, he bought all the remaining copies and burnt them. So it's highly unlikely that Lobachevsky or Bolyai would have seen this. But the uncanny similarity of this diagram to the diagrams found in Bolyai and Lobachevsky suggests that these ideas were in the air. As Bolyai's father said to him back in 1823, many ideas have an epoch in which they are found at the same time in several places, just as the violets appear on every side in the spring. Farkas wrote that to János, telling him, go ahead and publish because somebody will get there first if you don't. And why would they know about this? Well, In fact, Lobachevsky was perfectly aware that the equations of hyperbolic geometry were very similar to the equations of spherical geometry, and he pointed out that by changing k to ik, you can go from one to another. Bolyai himself had derived the identities of the hyperbolic plane. So I don't think it's inconceivable that mucking around with these ideas, they'd actually found what it was they were looking for, namely the identity of parallelism, and then they set about looking to prove it, only they proved it in entirely different ways. And I suppose finally, the coincidence between their work raises, doesn't it, the age-old question of whether mathematics exists outside of mathematicians waiting to be discovered, or whether it's inside mathematicians and is invented. It would appear that Bolyai adhered, like Sir Roger Penrose, to the first view. He felt that mathematical truth was out there, and it was true whether you were in Kamchatka or in Mareshvarshahi, and it was waiting to be discovered. And others disagree, but maybe that's a topic for another day. Okay, thank you very much.